subtract. So we're going to use our calculator. I'm going to show you a nice feature on the calculator to help us solve this. We're also not going to make a table of values. I have all these points to fill in here, which are a lot, so we're going to do this in a slightly more efficient way. To get the slope of each line segment we're going to draw in, we have to add the x and the y value together. Well, the easiest sum is 0. So right now I'm just going to start at the origin. When I add 0, 0 together, it's going to give me a horizontal tangent line or a slope of 0 here. Where else will we get a slope of 0? At what points? Hopefully you guys are thinking when x and y are opposites, right? So if I go over to 1, -1, I'm also going to add those together. We'll get a horizontal tangent line, a slope of 0. At 2, -2, at 3, -3. So it looks like they're forming along a diagonal here. So let's proceed up and to the left. At -1, 1, we have a horizontal tangent line or slope of 0. At -2, 2, same thing, and then at -3, 3, same. So down here at the end of the diagonal, I'm going to show that we have a slope of 0. Next, let's go over to the ordered pair 1, 0. So if I add those two values together, I'm going to get a slope of 1. So I'm going to line it up this way. We'll say a slope of 1. Where else? Will this also happen along a diagonal? If I go over to 2 down to -1, I get a slope of 1. Same thing here at 3, -2. So again, it looks like diagonally this is working out. At 1 or 0, 1, I'll have a slope of 1. At -1, 2, I'll have a slope of positive 1. And then at -2, 3, I'll have a slope of positive 1. So again, we always want to write it out what our slopes are as well as drawing them in. At 2, 0, I'm going to be a little bit steeper. I'm going to have a slope of positive 2 here. Line it up with this point. At 3, -1, I'll also have a slope of 2. So it looks along this diagonal. 1, 1, I'll have a slope of 2. 0, 2, I'll have a slope of 2. And -1, 3, I'll have a slope of 2. So we're going to continue in this fashion. Looking at now 3, 0, I'll have a slope of 3. I can line it up with this point, so a little bit steeper. Going along the diagonal at 2, 1, I'll have a slope of 3. 1, 2, I'll have a slope of 3. And 3, 0, or 0, 3, I'll have a slope of 3. So we have a slope of 3 here. Let's go over to 3, 1. I'll have a slope of 4. Again, just as well as you can draw this in, lining it up with your ruler will be the best bet. At 2, 2, I'll have a slope of 4, and at 1, 3, I'll have a slope of 4. Our next point at 3, 2, we'll have a slope of 5, so let's just make it a little bit steeper. And then at 2, 3, I'll have a slope of 5, so writing that in. And then up here at 3, 3, we'll have a slope of 6. So again, let's just write this in. I don't want to make it look too vertical, but again, a little bit steeper than before. On the other side, we should just have the opposite. So if I go over to -1, 0, we're looking at a slope of -1. So it's going to start to look like this. At 0, -1, we'll have a slope of -1. At 1, -2, we'll have a slope of -1. And at 2, -3, we'll have a slope of -1. At -2, 1, we'll have a slope of -1. And -3, 2, we'll have a slope of -1. Now this is starting to look a little different here. Not that the directions are going to be opposites, so let's continue this, and then we're going to use our calculator to not only solve it, but to graph it as well. So let's go over to the ordered pair -2, 0. Adding those two values together, I'll get a -2. So kind of lining it up with this point. Also at -3, 1, we'll get a slope of -2. -1, -1, we'll get a slope of -2. 0, -2, we get a slope of -2. And 1, -3, we get a slope of -2. Continuing here at -3, 0, a slope of -3, kind of lining it up with this point. Likewise here at -2, 1, -1 rather, slope of -3, -1, -2, slope of -3, and 0, -3, a slope of -3. All right, at -3, -1, we get a slope of -4. Down here at -2, -2, and -1, -3, slope of -4. Our next two along the diagonal should be at -5, making them a little bit steeper, or just writing them in. And then at -3, -3, we'll get a slope of -6. So right now it might be tough to determine how we're going to draw this in. If we pick a point somewhere along here, notice it might catch, and right here at the horizontal tangent line, it looks like it might curve up. And then if we cut it on the other side and follow these, it looks like it's just kind of curving down, that it's not going to curve to go back up again. So let's take a look at this. On your calculator, just go to a calculator page on your Inspire. And then go to Menu, 4, and then go down, scroll down to Option D. It should say Differential Equation Solver. So select that, and as soon as you do, you should see a D solve come up. And then in parentheses, you want to go ahead and hit the Y button here. And then we need a little prime. So if you go to the button next to the G where it says question mark, exclamation point, it's in the top row, second from the end, a little apostrophe or a prime symbol that we're looking at there. Then go ahead and hit the equal sign, type in x plus y, comma x, comma y. And as soon as you do that, you should get an answer of y equals c1 times e to the x minus 1. This c to the 1 is just a coefficient. We could just call it c, or we could call it a. Now what I want you guys to do is go to your calculator, and let's pick some values for a. So we don't need to type in the slope field here. We could maybe give it a try. So no, it wasn't working for two variables here. But just go ahead. Let's pick some values in for a. So right now, just on a graphs page, type in, let's say a is just 1. So type in just e to the x. Let's say a is 1. So e to the x minus 1 and see what graph that looks like. And then maybe say, hit tab and go where a is negative 4. So go ahead and type in y equals negative 4 e to the x minus 1. And pause this while you're doing this. I'm going to go ahead and scroll down next to show you the graphs that I'm getting. So as you go ahead to do this, these are the two results. Notice the different directions here. So when a is a positive 1, we're getting this blue curve. Notice they kind of start off at the same up here, but then two directions. And I'm going to bring this up, superimpose this over the slope field that we have here. Try to line it up as best we can. So if I maybe went right to the origin here, one of my horizontal tangent lines, notice if I'm coming down here when a was at positive 1, it's hitting this horizontal tangent, that's what's turning, and then it's sort of going up along the other slope line segments here. But if a was a negative 4, notice how it's kind of getting hooked into this direction that's right here, and then it starts to gradually curve down as well. So those are the two ways that we could look at this and you could check. So some of these we can't solve algebraically by hand. You can use the calculator for this, and chances are you're going to use it when we see a sum or a difference of two variables here where we can't use that separation of variable to help out. All right, the next two pages involve matching here. We're going to be given our slope fields already graphed for us, and then we have to sort of match either with their differential equations or with the equations of their functions. So for 10 through 17, these are the choices that they give us at the bottom, and then this is just the image for number 10. So look these over. Notice all of these say dy over dx, and then look at the slope. So go ahead and pause this for a second and see if you can eliminate any possibilities and kind of narrow it down. But what we're looking at here is all of these slopes right now are different. So we know the slopes aren't constant. So also we're looking at that, yes, we can't say any of the slopes are going to be constant. So right now we could rule out J. I believe that's it. We also know they're not linear because they do curve right here. So if we were to draw in our function, the curve I'm going to draw in is of our function y. So based on this, I could say y is quadratic, which means y prime, or dy over dx, if we take the derivative of any quadratic, we're going to get a linear function. So we're looking for dy over dx to equal something that's linear. So right now, that rules out b, that rules out c and d. Anything even with two variables here, that could rule out h. Even with it equaling a y, we could rule that out. So g and I as well. So we're narrowing it down here. And to rule out a and f, because those are just opposites here. So let's see what would make sense here. So dy over dx is equal to x. Well, if x is 0, dy over dx would equal 0, and we definitely don't have that there. Same thing for f. So here it would make sense. Our correct answer is going to be E. If you took each x value, multiplied it by a half, and subtracted 1, so let's see, at 0 here, or even over here at 1, if we took 1/2 of 1, it's just 1/2. 1/2 minus 1 is going to give us a negative 1/2, and that kind of looks like what this little line segment is right here, or getting closer to it. If we went over, let's say, to 2 right here, 1/2 of 2 is 1, 1 minus 1 is 0. So when all the x's are 2, look at how we're getting the horizontal tangent lines. So that's how we could do process of elimination to narrow our search down to for our answer a lot quicker. All right, a little bit different with the next set. Here we're given the slope field still. It says match each slope field with the equation that the slope field could represent. Notice all of these are now no longer written in dy over dx. They're either x equals something or y equals something. So if we were to draw in what we're looking at here, a couple ways to look at this. We know that if we look here, y prime, which is equal to dy over dx, what we're looking at here is these all look to be constant, right? Right, this way. It's like equals a constant. Now, if our derivative is a constant, that means our function is going to be linear, because the derivative of a linear function is a constant function. And if we were to draw in a specific solution for a line, we're kind of looking at something like this. So we know we're looking for something in slope-intercept form. So we could rule out A is that y equals a constant. B would be a vertical line, x equals 2. Y equals x, that's a positive slope. This one definitely has a negative slope. Y equals negative x could be a possibility, so we'll leave that there. Y equals negative x squared, that would give us a quadratic or a parabola. This is a cubic function. It's definitely not, h and L are actually the same. It's definitely not a trig function. It does not look like a natural log curve or e to the x curve. Definitely not a y equals 1 over x, a rational function. So this does limit us to just y equals negative x. So if I were to look at positive 1 here, or actually at the opposite of x, so yeah, x is equal to positive 1, y is equal to, or dy over dx is going to equal a constant here, is what we're looking at. So all of these look to be at a negative 1, so we could write this in, that dy over dx looks to be at a negative 1. The antiderivative would just be a negative 1x plus c. So we're looking at the correct answer of D. Some of these take a little bit of reasoning through, so make sure that you're trying to eliminate things that you know for sure are not going to match. And then once you do find it, take the derivative of it and see if it does match every value that's showing up here.